for example 4, right? Class example 4, right? Of course, some of you will just plug it in, but if you were to make use of the earlier theorems, you could just break up this into the difference of the two limits, and then you can evaluate 4a. Likewise, for 4b, the same thing goes for 4b. Of course, you say, hey, I could just plug it in, nothing's wrong, no, there's nothing wrong. Or if you want to, you can just make use of the earlier theorem and say that this becomes the limit of the numerator divided by the limit of the denominator. And then in this case, you will have 4 plus, and that gives you 5. I am almost sure that those who watch the video, you have done it on your own, right? You got a value. Just that the way you have gone about it might differ. Right? YouTube is on YouTube. I posted it on YouTube. You don't have to subscribe, you don't have to. You just. Yeah, sure. Just it's not the best in the world, but you feel that it's useful for somebody else, just go ahead. I'm alright. Just sleep. Okay, for the number five, right? You realize that in the case of number 5, we cannot just plug it in, because if you plug it in, it won't work. For number 5, because you have the so-called this indeterminate form. If you have a 0 over 0 is the indeterminate form, so class, you would have tried and remove it by taking the factorization of the numerator. And then, now let me ask you this question, class, why is this cancellation valid? Well, because x never 2, you see. That's why the cancellation is valid. And this gives you 4. Okay, then for the next one, the same thing goes, because if you were to put in 3 right into the fraction, you're going to run into an issue. So you want to do some factorization. And again, upon cancellation, you have this, and then now you're ready to plug in the value. 3 over 2. Right, this is example 5. Right, I'm almost sure that all of you actually got it correct, got it correct. Okay, in the case of example 6, right, now you would have read the example and realized that to eradicate the so-called indeterminate form in the fraction, one way is to do it like this. There are people who do it this differently, There are people who do it. Okay. Right. You could factorize it like this, Sorry. Hello. Yeah. You go to the general office. Sorry. You go to the general office and look for Miss Lynette. Yeah, general office. Yes, please. Okay. Sorry. Sorry about this call. I deliberately waited for this call because it's something very important. The vendor is here to settle some matters. So that's why I need to take this call. So I'm going to silence my phone now because I've already given him the right person to approach. Sorry about it. Okay. Thank you. You can done it this other way, you know. You can done this other way, and this gives you also root 1 plus 1, and this is 2. So example this can be done this manner, right? Okay, a show of hands, who haven't tried example 7? Just a show of hands. Who haven't tried example 7? It's okay if you have not tried, just let me know, no? So I know that there are people who haven't tried, and therefore I can slow down for you, no? So no hands raised. I will assume that O2 is capable.
Yes.
Yeah, right, Ethan, best class ever. Right, Ethan, right?
Yes.
Yeah.
Yeah.
Okay. This one, let's go to the squeeze theorem. We need to discuss this a bit, even though you have watched the video. I want to highlight to you, class, in using this theorem, you got very careful, you know. To be careful of what, you know. So for example, to do this question, right? To do example 9. Right, to do example 9. To start off with, you will say that sine 1 of x, right, is between 1 and. The next step you do is minus x squared. That side is very noisy. The corner there, what's happening there? You tell me what's happening there. Okay, so yeah, this line, right? There's a high chance that some of you might write this as the next line. Class, I want to stress, you know, we do not want students to write a line that's like this. Please do not write this line like this, because when you write a line like this, right, you're presuming that the limits of these three functions are already defined. So we do not want you to write a line like this. So please refrain. Okay, don't that again. So what you should do is to say since the limit x goes towards 0 of minus x squared is 0 equals to limit as x goes towards 0 of x squared. Therefore, by okay, over here I write ST, means squeeze theorem, of course, but you want to actually spell out in your own working law. Yeah, limit x goes towards 0 of x squared I want to caution you, know, if in the exam you write the things in green color, you get 0. What did you do?
I multiplied the limit. I multiplied the limit. I took it as I separated the
Okay. So there's an opinion here. Can I have silence at the side? A bit noisy. So an opinion given here is like this. Right, an opinion given here is, and she says regardless of the second limit, because the first limit is 0, she said therefore the entire limit is 0. This one, I want to caution, this one is totally wrong, you know. You can't do this, no.
Yeah, it's 1 over 0.
No. More because to be able to write from this line to this line, there's a condition that's needed, no, that both limit must exist. In the event that you're not sure, in this case, you can't do that. You know, you can't assume that you can always change the limit of a product to become the product of the limits. It's not allowed. No. So that one's no. Okay. So you gotta avoid doing this.
No, but it does exist, right?
No, but
You
sine
use like
difference at
6
A is
zero
sine
on each
1
one
over
seven.
x.
Okay, so you're saying that this limit exists, right? You're trying to say, right?
Yeah.
Actually,
Negative 1 to 1.
actually, no.
No, it doesn't.
No.
1 over
No.
0. As long as you divide anything by 0, even if it's within a sign.
If you draw the graph, you find that near 0, right? It fluctuates very quickly, you know. It doesn't have. So it's not true. That one is not true. Right? Okay.
Wait, what time do you use squeeze theorem on that one?
On this one,
Yeah, because it.
okay, so now you're saying that use squeeze theorem on this one, right? So if I will take what you're saying, let me see. So you're saying this limit x goes towards 0, sine of, okay, let's hear from our friend here. How do you want to use squeeze theorem to establish?
Negative 1 and 1.
So you start out by saying this.
Oh, but it's like different. Okay.
Okay, different, huh?
Yeah, okay, it doesn't exist. That makes sense.
Okay, the next one is this important result that you saw in the notes, you know. Although it's written in this manner, class, it is pretty much the same as having written in this other manner. It's the same, you know. It's the same, right? Shh. If you have viewed the video or you have read the notes, right, you realize that there is a geometrical consideration given to you here, and then using the squeeze theorem, you manage to establish this result. So far, right? So far in the whole AP exam history, they never ask you for the proof. But actually, it's not rocket science. It is geometrical coupled with squeeze theorem. Right? So you just use these two, you can prove this result quite readily. So with the result that this limit is actually 1, we can then venture into solving a question like this. Example 9a. Who have not tried? Okay. Thank you for that. So let's do it together. Okay, this gives you limit. Right, and this gives you limit x goes to 0.
Are we supposed to show that sin x over times 1 over cosine x equals to tan x over x?
There could be other way to present it, but one way is to do this.
Are we supposed to show the way to derive sin x over x?
I don't understand what you're saying. You want to write on the board?
Are we supposed to derive the way you find out sin x over x?
No. You can make use of result now. You're supposed to make use of the earlier result. Right. So what happened is, I have rewritten this one as this. And then this gives you 1 times 1, and therefore is 1. And then for the next one, right, you can rewrite this thing as like this. Sine 2x over, and then 3x over sine 3x, and then you have 2 over 3, and then you can break this into and that gives you 1 times 1 times 2/3. and just tilted. Not at the moment. Someone raises the use of L'Hopital's rule. I would not advocate it at this moment. We'll use it later in chapter 2, okay? We'll use it in chapter 2. Yes.
So that basically means that
Yes. Yeah. Someone clarified this, no? You can readily apply this result without proof. This is a deduced result. Okay. Whether it's a phi x. Okay. How does this what does it how does it think okay, there is a you are not wrong, you know, just that you didn't give enough substance. So there's a question raised. If you have sine 2x over x, right, sine equal to x, she is right. She says the answer is actually 2. But this one requires a little bit of justification, you know. You want to write this as limit x goes towards 0 of 2 times sine 2x over 2x. What's important is this number and this number must be identical. Then only it goes to 1, you know. So then this becomes 2 and then 1. That's why it's 2. Okay, so that is our example 9. So in example 9, I would not advocate the use of L'Hopital's rule. Yes. That's L'Hopital's rule. Yeah. Later on, yes. Expand. Yeah, it works. Yeah, it works. If you apply Trigo method to tidy up, it is acceptable. No? It is. It's a good solution. But it's harder, isn't it? Because you know the Trigo identity.
Yeah, all the
like the sine 3x, the sine 3x, the one. Yeah, you need to know it. Okay, you can. Okay, now having understood the two-sided limit that we did just now, now we want to talk about one-sided limits, you know. Class, we're on this page. Okay. On this page, we want to introduce to you the concept of one-sided limit. Can someone tell me the meaning of this notation? Yeah. Right. X approaches A from the left, and then X approaches A from the right. And the boy behind. Very noisy. Jethro. Can you sit here? Can you take a chair and sit here? Can you sit here? Can you sit next to me? Bring your chair and sit over. Jethro, yeah, bring your chair and sit here. Can you bring a chair and sit here? Until I am very sure you can mellow down a bit so that my class can go on. You are distracting my class. Jethro, okay, since you don't move forward here, yellow card. The next round you do it, I'll insist already, okay? The next time you create noise, I'll insist. Your distributors are very loud, you're very loud. Okay, now class, when you write a statement that's like this, right? When you write statements like this, you want to know that this refers to the two-sided limit. And for this two-sided limit to exist, what this box says is the left limit and the right limit must exist and they must be identical. Then the two-sided limit is deemed to exist. So let's look at this example 10. Okay, example 10, I'd like you to sketch the graph for example 10. Can you all now spend some 30 seconds to sketch example 10?
Yes.
Can I see your work?
Are you that hot right now?
Yeah.
You can bring a table also. Bring a table. You can borrow a table. Yeah, I borrow a
Okay, sorry. I'll still go for you. Thank you. Stay on the bed. Go on right now.
Do you have some paper to spare? Any of you have paper to spare? Join your table this way. Do you have some writing paper to spare? Do you have some writing paper to spare?
Earlier there was let's just get tan x minus tan 0 over x minus 0.
Say again.
Now let's get tan x minus 0, tan 0 over x minus 0.
And then?
Which is the differentiation thingy.
It's true. It's
Yeah, you
true.
just did that method. Does that work?
It works.
Like, can you use
Okay.
it?
Not at this moment, not chapter 1. So now draw this graph. Don't draw my book, no. I let you see this book. Okay. Okay, class. When you draw this graph, right? This graph look like this. Okay, shh. I need some orderliness in the class. So if you right, then I have to exercise some consequence So you have to be correct. It's okay to discuss, but you have to do it softly, because if you talk very loudly, you are happy, but it may be affecting others, especially.
Yes, sir.
Okay, so the graph looks like this. Such a function is called a piecewise function. there are altogether 3 parts to this graph. Lesser than 4, at 4 itself, and then more than 4. In this question, you're asked to find the limit of the function. You asked to find the limit of function when x approaches 4 from the left. I'm almost sure for this question, a lot of you will write down the answer right away. But I prefer not, I prefer that in this case, I prefer that you write one more line before writing down the answer. I know that you know it's 2, but I want you to know that I prefer that you write down this as 6 minus x first. Because then I know that you have understood the meaning of x approaching 4 from the left, because you are using the function 6 minus x. And then this gives you 6 minus 4, and therefore is 2. Likewise, for the right limit, as x approaches 4 from the right, is x minus 2, and then I want you to write as 4 minus 2 equals to 2. When x approaches 4, in this case, what do you think is the two-sided limit? It is equals to, I was wrong, I was kidding, 2, right? Why is it so? Because the left and the right limit are both 2, because the limit as x goes towards 4, okay. Jethro, if you need to turn the table around, just go ahead, Yep. Right. This is how I should write. Now, so if you immediately write down 2, 2, and 2, you're not wrong, but really you want to actually write like this, and you want to provide a reasoning, And at f of 4, in this case, right, the function is defined to be 0 when x is 4. In this question, right, you want to notice something, The left, the right, and the two-side limits are the same. They exist and they are the same. Now you see that in this case, right, the function value at the point in question differs from the limit. And when such thing happens, you realize from the graph that the graph is what? If I ask you to give a word to describe this graph, you will say that this graph is discontinuous. Or you can say it's not continuous or discontinuous. So it has a brokenness, so therefore it is discontinuous. And then that brings us to example 11. And very quickly you realize that example 11 and example 10 are identical, apart from the value of the value of the function at x equals 4. So if you were to draw the graph of gx, the graph looks like this. It's now very nice. Right, it's all very nice, no brokenness at all. And then when you find the limits, you find that in this case it's very nice. They all match. So when they all match, you realize that this is a continuous function. Okay, continuous. There's no brokenness. Yes, sure. All the best, Yep. Earlier one got. This one don't have. Earlier one has.
What's the value at like?
This is defined. That brings us to example 12. Okay, class, can you now sketch example 12? You need to go toilet, so. It's a bit warm, it's true, but I will just tolerate for the benefit of some of those who feel cold. Yeah, I'll just store it.
The constant change in temperature is messing with her.
It's messing my body thermal actually. Why do you have the fan on?
It doesn't, the fan doesn't affect.
It's okay. Really?
Ah, it's cool.
Jethro feel cold. Is it? Let's see. Let's say for okay. Okay, class. When you finish sketching the graph hx, I'll turn on the fan. I'm very sus. Sorry, the two boys behind are very sus. What are you doing? You're drawing the graph now. Okay. Not me, the two boys. Okay, can you sketch the graph, example 12? Please slip of the tongue. Who is your mentor? Wong Teck Hee. Okay. Okay, so okay, can you try to draw a graph and then make a comparison? Why is it like that, right? It comprises 3 parts. To the left of -1, you draw the straight line between -1 and 4, the curve, and then more than 4, the line. While you try to draw, I'm going to walk over to look at these two boys' work. Okay. Let us be sure that you know. You see your graph? Hey, did you apply for my science fair? I advertised some science fair. The ASRJC science fair. There's also the Australian science fair. Are you applying? Oh, the Australian, if you don't have project, you still apply. The Australian, because maybe other people got projects to go with you.
Wait, no project.
The Australian one, the if you don't have project, just put new line. Okay, the graph. Are you ready to see? Okay, this is how it looks like. If you get a graph that looks like this, give yourself 2 taps on the shoulder. You did it. Right, to the left of -1 is a line. This is a line. Yes.
My IP died, but let's talk
-1 to 4 is a curve. The gradient. This one is it? Okay. So I'm asked a question. Okay. Let's check again. Let's check the gradient just before 4 and the gradient just after 4. Someone pointed out that I have drawn this thing wrongly. I think he's right, you know. I think he's probably okay. I think this case sorry, what's your name? Rayson. Okay, let's check again. I think that they are the same. Okay, let's see why again. if you were to differentiate this, you get 1 corner. So you put a number very, very near to 4 on the left, what would the gradient be? Almost 1. Right? Likewise, for numbers that's, yeah. So therefore, class, I wish to declare that this graph is correct. Let me give you a word, okay? Right, smooth. Okay. He was actually debating whether I should draw it as a if it's like this, right? There's a name for it, for this kind of joint, you know, cuffs. Okay, a sharp turn. All right. So in this case, it is actually smooth. Okay, we have verified together. That means they join nicely. Like this one, there's a sharp corner, right? Sharp corner. They didn't join nicely. There's a corner. Okay, so having sketched the graph, you now want to actually answer the question. You want to see the graph again, is it? You need to see the graph again? Okay, this is a graph. Okay, how do we tell it's proof? Okay, so if you differentiate this one, you get x over 4, right? You put in number that's very, very close to 4, but just before 4, it is almost 1.
You have to do that whenever you're given a graph.
It's good. It's good. But if you overlook and draw it as a cuffs, sometimes we'll just forgive you for that, because sometimes you're not careful with it. Sorry, what's your name? The girl's name. The girl's center. Yeah. Okay, Chun Hui. So you check the gradient slightly to the left and slightly to the, and you find that they are identical. Okay, Ryan, offensive is it? Rayson, oh sorry, Rayson. Rayson, okay. There was once a class, they swapped name in my lesson, and then I get very confused and I recorded the score the other way round, you know. Even do that, right? You do this in this class. Okay, let's answer this question. How do you answer this question? As x tends towards -1 from the left. And then you're not going to write down the answer right away. You're going to say this is limit x tends towards -1 from the left. So you put this in as 2x first, and then this gives you -2. And likewise, you're talking about limit on the right, you should be writing on the right of -1 is 1 over 8x squared, and this gives you 1 over 8. And then you ask for the limit at x equals to -1. What is your answer? Let's hear from the boy behind with the blue thinking. Does not exist. Why does not exist? Does not exist because the left limit. You need to have this habit of writing it down. Hx is not equals to the right limit. You must say the reason clearly. And then when x is -1, according to the definition of the function, this becomes what? 1 over 8 minus 1 square, which is Therefore 1/8. Okay. Then once you're done with this, you can try the next set of 4 limits. Okay. As you are doing the part C, I want to tell you that we are going to have a first grade task on the 27th of January. It's 27th of January. CNY is 20, 21st, and 2nd half period. So it's immediately after CNY. Immediately after CNY.
The scope is what?
The scope for the grade task is page 1 to page 21. Yep. Okay. There are people who are still taking it, so it will take a little while to tell you your score. You won't get back the paper. Diagnostic test, right? You won't get. You get to know the score.
Can we like know what we got?
Sure.
Can we know what questions we got?
Okay, I'll think about it. Okay, part C. Part C. Part C. Can you now do part C? Okay, as you do part C, let me go around the room to see that the guys behind are doing their work. Let me see your part C. Brilliant. Where's part C? Do you find voice here noisy? Yeah, the right, you just tell him to better now.
I did all my work.
Okay,
I
good.
don't think I'm even though I didn't do it.
Oh, good. What happened to the notes?
He left it morning. Yeah.
The pausing, Okay, that is part C of number 12. Hey, you finish it, yeah? Let me see your part C. Okay, thank you, thank you. Okay, 13, okay? 13. 13 is a word example. In question 13, 3 graphs are given to you, but unfortunately they're named the same, you know. They are named as fx, and fx, no. They're named the same. In the first instance, right, you can see that for the first function here, it has the left limit and the right limit, but the left limit is 1 and the right limit is 3, and the function value is 2. So this one scenario. Another possible scenario is the left limit at 1 and the function value itself are the same, but different from the right limit. And in the third instance, it shows you that it has a left limit of 1 and a right limit of 3, but the function value at the point is undefined. So this 3 graph, thank you, wants to illustrate to you that anything is possible. So do not be presumptuous, you know, that it must be like that. Anything is possible, right? Let's for example 13. Okay. 14, okay? Okay, let's say together. Question 14, class. What is the left limit equals to? Can you echo back? The left limit at x equals a? The right limit at x equals a? Is the function defined there?
No.
Yeah. So this is another instance, okay, of a different scenario.
OMG.
Okay, now the exercise. Can you try this exercise? Okay, not that. Funny, the height. Okay, for the exercise, once you've done it, let's make a comparison. So you can compare the answer. So these are the answer to this exercise. Okay, moving on. Okay, this is this one is a little bit harder now. In this question, right? In this question, you are asked to prove this. Okay, for this question, right? For this question, you're asked to give a proof to this statement. Some people say it's obvious. Some people say okay, because it's obvious, you know. And because it's obvious, they find that sometimes it's very hard to prove, no. For beginners, this ought to be seen as not so obvious. You got to pretend it's not obvious, and therefore you want to provide a proof for this. Alright, so we want to prove this by breaking up this into cases. Case 1, when a is more than 0. So if a is more than 0, this limit that you are working on. Okay, tell me why is this true? The girl who threw the pink thingy to the back. Yeah. Why is this statement true? Shh. When a is positive, why I have written that thinking? Because when a is gone. Okay. Right, because the way to explain this is because I know if a is strictly positive, those values of a, those values of x that approaches a, right? Like this game, those values of x that are near a, these values of x are something like this here or like this here, right? Because a is positive, values that approach a will also be positive. Therefore, x is positive, and therefore the absolute value of x is just x. And then this is a. And like to, you can write this mod a. What is after my lesson? Lunch. Okay, I'm going to finish soon again. Okay, to finish this quickly, can the same girl tell me what will I write? Sorry, what's your name? I cannot just call you. What's your name? What? Ting Wei. Ting Wei. When a is negative, tell me what's the next line I'll write. Right, you got this as x tends towards a, negative x, and this gives you negative a. And because a is negative, this is the same as right. So we have proven it to be true. Now, when a is 0, you can't do what you're thinking, you know. When a is 0, right, you can't write this as right away, you know. Brilliant. Right, you can't immediately say when a is 0, right, you can't immediately say that you can't do this now. Listen, shh. The reason is because at x equals 0, this function is defined differently on the left and on the right. So don't write this, no. You cannot write this immediately. Class, you have to write this. Are you ready?
Yes.
Always ready.
Wow, I wasn't ready for that.
You have to find the limit on the right and the limit on the left separately, because 有已經 see it 啦。
有啊。
Because the function is defined differently at x equals 0, because of this, right, you define the left and the right limit separately and show that they're the same, you know. Then only you can make that conclusion. So be very careful about this. So the point I'm going to draw across to you is whenever a function is defined differently at a point, to find the limit at the point, right, you must always find the left and the right separately. Yeah, it is. Yeah, it is. To be rigorous, to be comprehensive, that is needed.
Joe, can you scroll right?
Go. Okay.
Oh, there? 0.
Okay, sorry to hold you back a bit. We will continue 16 next time. When I see you again tomorrow, right?
Yeah.
Okay. Right. Math is like a daily subject. I'll see you almost every day. Except on Tuesday. Okay. Right. So if you're done, you can just go for your lunch, you know.
Yes.